very much. So it is nice to speak at this meeting. This is actually the fourth, my fourth meeting in celebration of Hendrik Lenstra. Organizers for inviting me. If anyone here is going to organize such a meeting dedicated to Hendrik Lenstra in the future, then I would also be delighted. So, let me explain what is a cyclotomic ZP extension. So I take P of prime, and I take it different from 2 to simplify matters. Then if you, then there is the cyclotomic, this is a P to the n plus first root of unity. This is an abelian extension. There is a subfield Q zeta P. And here there is a subfield of Qn. This extension has degree P minus 1. This extension has degree Pn. It is unique. And Qn is contained in Qm if m is larger than n. And that is the fields Qn. So maybe I write it like this. Q would be Q0 is in Q1, in Q2, etc. This is the cyclotomic ZP extension of Q. Called the ZP extension because it is Galois. If I take the union of all these fields, let me call it Q infinity, then this is an infinite Galois extension of Q, and the Galois group is the group of additive group of the p-adic integers. This is the cyclotomic ZP extension, and now you can compose it. If f is any number field, then you can consider the cyclotomic ZP extension of f by composing it with these all these fields. One is degree p over the other. So Fn is by definition Qn times f, and this gives me the cyclotomic ZP extension of Fn. And then the main object of study of classical Iwasawa theory for in the number field setting is the study of An, which is the p part, same p, the p part of the ideal class group of the ring of integers of Fn. So so that we have these group they map to each other. H0 you can consider ideal classes of F0 as ideal class of it1, etc. And you get a system of abelian groups. It is actually better to look at the norm map, relative norm map, because the relative norm map is in the cases that I will consider, all these norm maps are surjective, and in general they are eventually surjective if the index is large enough. So this is the object of study, is how this behaves. So we have Hn, which is the cardinality of An, which is a power of p, is p to the en. And one is interested in the growth of this. Before I forget, let me introduce Gn. I hope you will remember this when I use it. It is the Galois group of Fn over Q. So this is a cyclic group of p to the n elements. It is the Galois group of this extension.
You mean Qn?
That's what I mean. Yeah. That is what I mean. Okay. Well, this field sort of got a boost when Iwasawa proved. When Iwasawa proved a result theorem. This is Iwasawa in the 50s, in 59. He proved he studied the structure of the limits of these groups as Galois modules, and he had a formula for En. So the statement is that given f, there exist integers mu classically called mu, lambda, and nu, such that his exponent En there is given as mu p to the n plus lambda n plus nu. And so mu and lambda are positive. It may happen that n is negative. What is?
But do you really number them correctly for Fn? Because the first few of those groups fields can be the same. And if you have your real p to the n, that may be p to the n minus something, right?
Or n large enough.
Yeah, but still, that doesn't. You allow mu to be a rational number then.
Well, in my case, the case that I will consider, the
All the degrees of p.
fields will be linearly disjoint. So F is linearly disjoint with the p-adic. F is linearly disjoint
From
the
Q
p-adic tower from all the Q.
But I think otherwise this is wrong.
Okay. So then I will assume.
Is this not true for any GP extension?
Oh yeah, maybe, but I'm not going to talk about any GP extension.
No, but I mean, then you number them from degree p square, etc. You don't want to have a number of degrees 1 at the beginning.
I don't understand.
No degrees at the beginning. If F is not linearly disjoint, there are a few ones.
Yeah, maybe, yeah. But
this cannot be true.
okay, sorry, but then something else is true. And but I will not consider that situation. Sorry that I am a little bit sloppy. So I will assume that F intersection Q1 is Q. That will always be the case. But you're right. Sorry about that. Okay, so that is the Iwasawa theorem. And then shortly afterwards, a student of Iwasawa, Greenberg, made a conjecture that this is in 71, that that actually, if in the case that F is totally real, a totally real number field, and let me always have this assumption just to be on the safe side, then both these invariants, these Iwasawa invariants, the first two I mean are zero. That mu is zero and lambda is also zero. So this is Greenberg's conjecture. And the one step was then made by other students of Iwasawa. So the theorem this is the famous Ferrero-Washington theorem. This is 1979. And they prove that if F is an abelian extension of Q, then mu is zero. That is so this means that, of course, mu is the coefficient of a very rapidly increasing function with n, and lambda is the coefficient of a somewhat less rapidly growing function. So this says that the class groups do not really grow extremely fast if F is an abelian number field, and if the ZP extension is the cyclotomic ZP extension. Okay, now I want to report on some numerical evidence for Greenberg's conjecture. So the easiest non-trivial case is the case where we take totally, let me say, the easiest trivial case is Q. If we take F is equal to Q, then it is easy to prove that all these groups are trivial. So then there is no lie. So all n are zero and nothing happens. So the easiest non-trivial case is perhaps the case of a real quadratic field. So F Q square root F, where F is the discriminant, it is positive integer, and also the conductor. This is an abelian extension of Q. So a real quadratic. And the prime is 2. The mathematics of the case that P is 2 is a little bit different, because 2 divides the degree of the Galois group of this field over Q. So I prefer the next one, that is P P is 3. I will take P is 3. And then the thing that I want to explain how we obtain it and the questions we have about it is a result that was obtained first by Paolucci several years ago and recently by Pietro Mercuri. So they checked. So for this field, we know that mu is 0. This is an abelian extension of mu. They computations prove that for f less than 100,000, actually lambda is 0. And so this is a mechanical computation, and it follows actually from a result that is. Oh, maybe let me say a few more things. So Mercuri also did computations for 5 and 7, and nothing exciting happens. The behavior, the statistical behavior seems really the same. And another student of mine, Pagani, he also proved it for P is 2 and F up to 10,000. Then the mathematics is a little bit different, but the statistical behavior of the various groups, it seems to be the same. Let me concentrate on this case. And what is really follows, what they actually did is much more. They compute. Oh yeah, let me say what it means that lambda is 0. I forgot to say that. If mu and lambda are 0, it means that En is constant and is large enough. So lambda is 0 is the same as saying that these groups they stabilize. They become under the norm map. Under the norm map, they become isomorph. And so you have from a certain n on always the same group. And this is the group that should be finite if lambda is 0. And it was computed by in all these cases. So I have a list of these groups. Actually, more than the group, it is a Galois module, and we have a description of the Galois module. So this follows from a table of the stabilized class group AN. You want it is the projective limits of that.
The question is,
Yeah.
in USL's theorem, is it effective, the point at which this equation starts being true?
This,
Can you say that there's a given f, can you say beyond n0, beyond which this,
I don't know. Well, there are issues. The problem that Hendrik pointed out is that you may have intersection with F, and that causes things. I'm not. It has been computed in several cases, and I'm not really sure whether it is. It can always effectively be computed. I'm not sure about that. Okay, so let me explain how this is done a little bit, and then show you the results. So first, if F is of this type, then it is a subfield of a cyclotomic field. It is a subfield of Q zeta F, and in Q zeta F we have cyclotomic units, and therefore also, and you can take norms of those things. So in F, we have cyclotomic units. And I say it now, and I hope you forgive me in a sloppy way what the cyclotomic units are, and later I will say it precisely what they are in my case. So they are essentially norms from the cyclotomic field to the quadratic field, and of 1 minus zeta F. That is what they are. And in fact, I will, if I take an Fn in my tower, then it is contained in Q zeta F p to the n plus 1. And in Fn, we also have cyclotomic units, and they are norms of these things. And these are actually units because the conductor is composite. Well, F is p. F is, yeah, that doesn't happen. So we have cyclotomic units, and these cyclotomic units have I call the group sig F, and it sits inside the unit group of the ring of integers of F, actually for an arbitrary number field. So this is a subgroup, and then there is a theorem that goes back to Kummer. And it can be, Kummer maybe only had it for conductor, prime conductor. And then the correct definition of cyclotomic units was eventually given by Sinnett. And correct means that this theorem holds. So the theorem is that the index of the cyclotomic units inside the unit group is finite. And that moreover, it is equal to the class number, or the apart from the two parts. So the
Here,
It's K.
not true for any.
K is real abelian.
oh yeah, sure. I first had F, so I forgot to say. Yeah. Okay. K is really big. And then we have that. So Hn, which is the cardinality of let me just not say this, the cardinality K, so K is a real abelian. And the cardinality of the class group is equal to the index to the cardinality of a finite group, which is the units modulo the cyclotomic unit times maybe some power of 2. Okay, so it means that the power of 2 will not play any role in what I will say. So we have equality of these two groups. So, and I have this in particular for K is Fn, for all n. So if I want to study how the P part of these groups, how An grows, then the cardinality of An is equal to the cardinality. So now I also introduce notation. Rather than writing O of Fn, I write On modulo the cyclotomic units, and this I call it sig n. This is for in the tower. So if I want to,
only the P power in there.
yeah, this is the P part, and here we take the P power. Yeah, say it. I don't write. So if we want to see whether the An stabilize, in other words, if we want to check whether or not lambda is 0, it is enough to consider these groups. And beware, this has an awful proof, this equality. It is not a consequence of an isomorphism or a duality. It is a consequence of a value of an L function. You compute the value of the L function in 2 different ways, and you get this and that, and they are equal. And in fact, there are known instances where these groups are not isomorphic, but they have the same cardinality.
But their semi-simplifications are isomorphic.
Is that true?
The semi-simplifications are isomorphic.
Is that true?
It's a consequence of inequality in the Grothendieck group.
Okay, I didn't know that. Okay. Well, in fact, we will see that in my case, they will become isomorphic high up in the tower. Okay. Okay, let me then define the cyclotomic units so we know what we're talking about. So I still have F fixed, so F is Q squared root F. I have an N at least 0, and then I define eta N. It is the norm from Q zeta F En plus 1 over Fn of zeta F P n plus 1.
How can you take that norm if there is no inclusion? Oh, sorry, there is. Sorry, I didn't say anything.
Yeah, so we can take this norm. This is a unit. This is a unit in O n star. And so this is what I call. Oh yeah, there is another thing. I take the minus parts because the cyclotomic tower of Q squared root F. Everything here is a module over this small Galois group here of order 2, and there is a plus part and a minus part. This is not plus or minus for complex conjugation, but plus or minus for the action of this group. And the invariant part are the groups in the cyclotomic tower of Q, and they are not of any interest. So I always take the minus part, and taking plus parts or minus part is very well compatible with prime 3. So I will take the minus part here. So that means that I divide it by its conjugate. So I hope this is readable and understandable. I take the sigma minus first power. So sigma generates the Galois group of Q squared root F over Q. And this is not the most economic way. This is maybe a square always or a fourth power or something like that, but it is not interesting for my end. So this is eta n. And eta n is the main cyclotomic unit in this story. So if I define the cyclotomic units, this is generated by eta n, but generated over a group ring. And the group ring is zeta p gn. So these are the p-adics. And so it is the zeta, it is generated by eta n over this. Maybe I should not write this. Over this group ring. This is the definition if 3 is inert in the quadratic field. So if the conductor is not congruent to 1 modulo 3, then this is the definition. And with this definition, this theorem holds. In the case that F is congruent to 1 modulo 3, maybe I should also say the norm maps the eta n's to each other. The norm in the tower maps eta n plus 1 to eta n all the way down to eta 0. However, in this case, the formulas of Sinet get a sort of a trivial Euler factor that becomes 0, and then you don't get eta 0. The norm is 1 all the way down to the quadratic field. So it is equal to, now I write it like this, it is generated by eta n and by eta 0 in this case. And eta 0 is simply the norm of Q zeta F over Q square root F of the 1 minus zeta F, and the whole thing, take the minus part. So you have to add that in this case. So by this, I mean generated over the group ring. And then we have two results. The first result is that, in fact, with this definition, this is the definition of Sinet in this particular case. So in this case, we have that the cardinality of AN is equal to the cardinality to the P part of the cardinality of the unit group modulo these subgroups. That's the first result. And another thing that is very important is that these modules have an extremely simple structure, the modules of cyclotomic units. So that is now there's not even worth. It's rather easy to prove. Is that the cyclotomic units? So this is a module over ZGN, and it is free of rank 1. And again, I may be sloppy here. Perhaps you have to tensor this with ZP and take the ring ZPG, and maybe I should say that. But the rest is. So this is free of rank 1. And then in the split case, so this is the case if F is not congruent to 1 modulo 3. If N is 1 modulo 3, there are 2 generators, and the structure is a little bit different, but it's also quite easy. In that case, the cyclotomic units is isomorphic to the augmentation ideal of this group ring times a copy of ZP. So it is almost free. This is if F is congruent to 1 modulo 3. Yeah. And now in this talk, I will, and I think I'm not cheating when I do that, I will show you the behavior, how it works in general. I will concentrate myself to this case, that f is not 1 modulo 3, and in which case this module is free. So today we have also all the theory in the other case. It's a little bit, there are little variations. It doesn't change much, but I won't do it today. So today we take f is not congruent to 1 modulo 3. Okay, in that case, we have these. Look at the following exact sequence. So we have 0 cyclotomic integers at level n, the units at level n, and then we have the quotient. And now I introduce the quotient. This is Bm, the notation. So we have Am and Bm, and Am and Bm have the same cardinality. Yeah. Now, you remember the sequence? 1 minute. Yeah? Now I go up. I go n larger than m. There I have the same sequence. Yeah. And now I take Galois invariance. So I take Galois. This is Galois of Fn over Fm. I take Galois invariance, and then I get H1 of Galois of the cyclotomic units. And by Galois theory, this is the sequence that we had before. This is the cyclotomic units of level m. It's easy to see that cyclotomic units behave that way. And the units also, and we get Bm. So this gives rise to 0 Bm goes to Bn Galois invariance. And this is trivial because the cyclotomic units are free over the group ring. So this is 0. So we see we have an isomorphism. So we see that the B0s, the groups Bn, they go injectively to each other, and the lambda is 0 conjecture says that this should stabilize. That is what it is. Another thing is, you see we have Galois theory for these things. So for instance, one corollary of this statement is that if B0 is 0, then what? Then everything is 0, because the Galois group is a P group, and a P group acting on a P group must have fixed points. So if there are no fixed points, then this is everything is 0. So then Bn is 0 for all that. And another thing that follows from this very easily is that if you have 2 consecutive Bn's that are equal, then they are all equal. Then
Equal to 0?
no, too enthusiastic for all m. Thank you.
At least n.
Greater than n.
Greater than n. For all n greater than n. Yeah. And this is just an application of.
No, the other way around.
Yeah, maybe I should say m here. Always larger than that. For psychological reasons, I will write it like that. And this is just an easy consequence of Nakayama's lemma. So I maybe don't show it. So this is just exercise Nakayama lemma. Nakayama is a theorem about modules over a local ring, and in this case, the local ring is ZP Gn. This is a P group, finite P group, and this is the p-adix, and this is a local ring, ZPGN, and the module is the BMs. So, and this opens the way to an algorithm to compute this. Because now what you could do, leave this, is compute these BNs in every state, level 0, level 1, level 2. And if at one point you find that B doesn't grow anymore, that B2 and B3 are equal, for example, then you know that it will never grow again, and that lambda is 0. So
We're assuming P is 3 here, right?
P is 3, yeah. Yeah, I write P all the time. I think it is more clear, but everything I think is true, also if P is not 3. So that's the algorithm. Is compute Bn for n is 0, 1, 2, until Bn is equal to Bn plus 1. And if that happens, hooray, then lambda is 0. And before I will explain to you how you do this, how we do it, and I will ask you if you have suggestions for improvements to our algorithm, because we are a little bit stuck in the big cases. Let me give you the results. And so we make a little table. So here we have F. So I will not write 1 modulo 3 in the beginning. So F can be 0 modulo 3, or it can be 2 modulo 3. And the behavior is exactly the same in both statistical behavior, but still I split it for you. So the number of fields in the range, now F is less than 100,000. There are 7606 fields that have their conductor divisible by 3, and there are 11394 fields that have the conductor congruent to 2 modulo 3. If a number is divisible by 3, it is more likely to be not square free. I guess that describes the discrepancy. Now, as I told you, the fields where B0 is 0, that means that A0 is also 0. And that means that P does not divide the class number at level 0. And that means that 3 does not divide the class number of the real quadratic field. In that case, there is no life. The tower is 0. So I say that in that case, it stabilizes at level 0. So there is nothing there. Okay, no, yeah. But I'm not interested in those. I'm interested in the one that stabilizes at the level larger than 0, higher up, that there is some tower. And I hope I don't make again an index mistake. The number of fields that have a non-trivial 0 level, that is what this means, are 769 in this case, and 1250 in this case. And you see this is about 10% that remains. That's the Cohen-Lenstra heuristics in this case. Predict that in about 11% or 10%, the class number of the real quadratic field is divisible by 3. So this is nothing new. So now let me look at the ones that stabilize at level 1 or higher. Yeah, this maybe. Yeah, this is stabilized at level 0. No, at level higher than 0. I'm totally confused. Let me write it in another way. This is the case where B0 is 0. Those are the ones I exclude. So this is those are the cases where B0 is not 0, where the class group is not trivial. Now we go to the next level in the tower and compute B1 there. How many are non-zero? We find 233 in this case and 423 in this case, which is about a third. And we keep doing this. B20 is not 0, etc. And I won't give you all the numbers, also because I don't have them. And if I go up to B6, yeah.
I thought that all these had to be non-zero once B0 is not 0 because of your identity. Your identity about BM being the Gallon variant.
Oh yeah, you're right. Thank you for saying that. Yeah. So I should say
equal to B0, not equal to B1.
Yeah, this is B1 not equal to B0. And this is B2 not equal to B1. This is B6 not equal to B5. Yeah, thank you, thank you. Well, if you look a little bit, this is about 10%. And this is about 30%. And that persists. Sometimes it's 35%, sometimes 25%, but it is roughly a third. So every time you lose 2/3 of the discriminants when you try to compute in the tower. And so what you expect at this level, then you expect the number of fields, which is about 20,000 divided by 10 times 3 to the 6th, which is like 7,000. You expect maybe 3 fields to provide this. And in fact, at this level, I find 3 fields in this case, and I find 1 field in this case. And after that, there is nothing anymore. There is no discriminant that has a larger tower. So no more example. And well, I do not explain you the situation for FS1 mod 3. It's a little bit different, but the statistics is exactly the same. So you really have the feeling that it is sort of random behavior, and the chances follow some kind of heuristics, and therefore lambda should always be 0. Okay, now I want to explain you how to compute Bn. First, a structure theorem about Bn, and actually in these computations, Bn dual is much more useful. So we have a proposition that so Bn, this means dual as abelian groups, so Bn dual. So this is a module over ZP-Gn, and the claim is that it is a cyclic module. So Bn is a cyclic ZP-Gn. So how do you prove this? Well, it is very easy. You write down this exact sequence, cyclotomic units, ON star Bn, and you multiply by e to the k for some k. You get a commutative diagram. And we can do the snake. And these maps are injective. These are just these are injective. There is no torsion. There's not one also. And if I take this large enough, if k is large enough, then this will be 0, because Bn is a finite group. So this is 0. And then I see that Bn is isomorphic to the co-kernel of this map. So I find that Bn, and this is Galois compatible. So as a Galois module, Bn is isomorphic to the cyclotomic units and modulo the cyclotomic units and to the p to the k. And if you don't like snakes, then you can also just write on the map the isomorphism maps epsilon. So class units modulo cyclotomic units to the p to the k power.
So why is that isomorphic? Do you not get the rest of the snake?
Oh,
or-
sorry. Thank you very much. It is an inclusion. Thank you very much. Thank you. Yeah. And now we look at this. We know that the cyclotomic units are free over the group ring. So this is free over another ring. This is free rank 1 over a ring that I call Rn. Yeah, maybe I should call it Rnk. It's a little bit. It's Zp to the kz. No, it is scaled by k, so it is a z modulo p to the k modulo gn. And this is a finite ring of p power order. And it is a local ring. It is a local ring, and it is a Gorenstein ring. And that is what is very helpful. So this is a Gorenstein ring. Gorenstein means in this case for these kinds of zero-dimensional rings that if you take the dual of the ring in the sense of groups, and so this maybe put a z here. So then this is an Rnk module, and it is because it is an Rnk module. And it's if it is Gorenstein if it is free of rank 1. Now in this case the action is if I have an x in the ring and I have an f here, then maybe not f. No, f is used a lot. I have a phi here, then x phi of something here, oy is phi of xy. That's how the action is.
Can you not right away dualize your top injection? And
Yeah, I could also do that, definitely. This is in fact what I'm going to do.
Oh.
But then I must know that the dual is isomorphic.
the dual of free is free over these rings. Yeah.
Over these rings. So
Okay.
I need some properties of these rings. This is in fact what I'm going to do. I dualize. So and this has a consequence. So this is a definition of Gorenstein, and it has a consequence. What Hendrik just points out now, that there are two notions of duality for finite modules over this ring. One is this one as abelian groups, but the other one you can take the ring here, and these coincide. So you have it's one of those formulas. You have something like home. This is the Galois group, so this is over the ring Rn. I take a module, and then I take the home of R and K.
In your proposition, which dual do you mean? There are two duals.
Yeah, exactly. Well, they are the same. And maybe the Galois action differs, but I just mean that I don't understand. They coincide, these two notions of duality.
Yeah, but you didn't. We didn't know that yet when you wrote it.
I'm going to tell you now. Seriously, I'm going to tell you. I thought it was implicit on your criticism before that you were supposed to know this. Okay. Okay. So we have this, and this is isomorphic. This is one of these standard diagrams, standard formulas in commutative algebra. Yeah, and now we know that this is free of rank 1. So this is isomorphic to R and K. And now we see, in fact, that these two notions of duality coincide. We have duality with values here, or duality as abelian groups, and they are isomorphic. There is a canonical isomorphism. Well, once you choose a generator of this one. Okay, now what I can do, and I will not check all the details for you. So these isomorphisms, this one here, it is compatible when I change the level, and I can glue it all together. Oh no, I should still take the dual of that sequence. Excuse me. So corollary, I take the Bn dual, which is also the home over R and K of Bn with values in R and K, and that is the same as, or this is admits a surjection. This is how do you say? covariant, so I get the homomorphisms of Rn cyclotomic units modulo cyclotomic units n to the pk Rn, and this is free of rank 1. So then we see that in fact Bn dual is a quotient of this. It's a cyclic module. Now you can glue all these things together. It's all cyclotomic eta n plus 1 is mapping eta n. Everything works out fine. So we get now that Bn dual as a Galois module is isomorphic to a ZP Gn modulo some ideal In. I also put p to the k, and the p to the k is contained in this ideal. This is as a Galois module. And this I have for all n's and m's, and I can glue them together. So I can take the projective limit of these Bn tilde, and that is actually the if lambda is 0, this is the Bn that stabilizes, but if lambda is not 0, then not. Then this is isomorphic to the projective limit of this here. So that is the projective limit of this ring, ZP Gn modulo some ideal. Now this ring is the famous ring in Iwasawa algebra. This is lambda, and it is known that lambda is isomorphic to a power series with coefficients in ZP. The 1 plus t here corresponds to a topological generator of the group Gn, and this is a local ring with maximal ideal Pt. And these rings are quotients of it. ZP Gn, you can write it as lambda modulo an element that this you can write it as ZPx modulo x to the p to the n minus 1, because this is a cyclic group of order p to the n. And then actually if you shift the variable to put the maximal ideal here, this is also a local ring, you get ZPT modulo 1 plus t p to the n minus 1 and orbit. So it's the same, and this element is called omega n. Yeah, so we see now that the stabilized, that this limit is isomorphic to lambda modulo some ideal. And the table that I mentioned you in the beginning gives you those ideals. It is a list of ideals. Oh yeah, and the formulas that I gave you for Bn, the Galois behavior, for instance, that the invariance of Bn at level n were exactly the Bm at level m. That corresponds to the fact that that if I call this thing, if I call this x, so x is the projective limit of the Bn dual, then at a fixed level Bm dual is x modulo omega m x, and so that is also cyclic. It is lambda modulo. Then I get the same things back. I get this ideal I plus omega m. Okay, now to how do you compute? So instead of computing Bn, I will compute Bn dual for n is 0, 1, 2, and then wait and see where it's stable. And how do we compute Bn dual? Well, I compute first Bn modulo p, and then Bn modulo p squared, and then etc. until it happens that Bn dual modulo p to the k is equal to Bn dual modulo p to the k plus 1. And this is the same argument as before. Once this is the same, it follows that this is killed by p to the k, and that from this point on, the group will be equal to Bn tilde. Yeah, so this means that Bn dual modulo p to the k is Bn dual. And then I'm done. So the only thing I have to explain to you is how to compute this. So that is now the following question. Compute Bn dual modulo p to the k. How do we do that? Do that using the same diagram. It's still here, so maybe I can use it. Except that I do not assume that p to the k is 0. After all, I will do this for, I don't know which p to the k kills Bn. I don't know. So I set it up in general. And now I can again apply the snake lemma. Now this, the same diagram. Apply the snake lemma. So this is still injective. So we get Bn p to the k, kernel element, the p to the k torsion goes in the sinusoidal units modulo p to the k powers, goes in the units modulo p powers. And now it dualizes, because these are all killed by p to the k. So these are R and K modules. It's finite Gorenstein ring. It's Gorenstein ring. So I take the rules, this is exact, they are finite groups, and I go the other way around. So I get Bn dual modulo p to the k, that is the dual of this. Then I get the dual of this, and this is free of rank one, So this is R and K. And now I get the image of O star modulo O n star p to the k. Or actually, no, sorry, I should take the dual. So this is Rn, and then here we have home Rnk. Yes, there it is. And this gives me a beautiful explicit description of the module I want to compute. My module I want to compute is a quotient of R and K modulo an ideal. And I can actually write down what the map is here. If I have a homomorphism from the unit group to Rn, vectors over to the k powers, which is automatic. Where does it go? Well, you have to evaluate it in the sinusoidal unit. And then you get an element here in R. This is the map. So the description of my module is it is B and this p to the k is isomorphic to R and K. And R and K is very explicit. You see, it is polynomials with coefficients modulo p, t modulo 1 plus t to the p to the n minus 1, and then we have all these elements here. All these homomorphisms that come from there. That's the description. And how do we now compute it? Well, you have to find these homomorphisms. You have to find elements in here that give this ideal. And so you need homomorphisms from the unit group to the group ring R and K. And where do we find those? Well, we find those as follows. So if R is a prime that is split in Fn and also Q zeta F, and is also maybe even closer to 1 theoretically, depends on K, this much, then I can do the following. I have my unit group. Maybe I should point out that this automatically factors over the p to the kth powers because this group has exponent p. So this is the same as it's the same. So I start with a unit, On. Then I take it modulo R. I go in the unit group. R splits completely in Fn. So this is the products over primes R that divide R in On. And then this is the prime field because it splits completely. So I get finite field Fr star. I go there. And now I notice that this group has order divisible by p to the k because of this condition. So these are all copies. I can go to the modulo p's powers. Let me do that. Modulo p's powers. P to the kth powers. Now all these groups have order p to the k, and the components are permuted by the Galois group because the R is completely split. So this is just as a module isomorphic to Zp to the kz and then the Galois group. And that's R, that's my ring R. So you see, combining all these things, I get a homomorphism here. And guess what? Those are all. And that is essentially, or not essentially, it is a little bit of Kummer theory and Chebotarev density theorem. This actually, I call this element Fr. This is the Frobenius for that prime R. So what we actually have is that this module is isomorphic to this modulo the ideal generated by the F to the R. And this is all very explicit because you can put this on a computer. It is computations with polynomials, and you have an ideal generated by polynomials with coefficients in a finite ring. So that's what we do. And then they have a second problem, which is actually similar to this problem, is that when do you stop? No, actually, sorry. There is a problem now, is that how do you know that you have computed enough FRs? You have to compute infinitely many, but you can't. So you have to stop at one point. So at one point you stop, and then you believe that what you have found is the whole thing. The provisions then actually, yeah, it's the whole thing. But you're not sure. But you continue the computation under that assumption, and you go up in the tower. So once we have computed V0 dual and V1 dual, we go to V2 dual, and we repeat the same thing. So now I compute the V1 dual, V2 dual, and go on. But I'm not 100% sure the answers are correct. But at a certain point, I will find equality. And then I know that the tower stops if these answers are correct. And how do you prove that it is correct? Well, fortunately, one bound I know. It can happen that this ideal is too small. And that means that the module that I compute is actually too big. And then, so I have to show then that now I'm confused. Come on. Yeah, it could be too big. And now so what I have is the following. I have a candidate because every time this is isomorphic to the group ring modulo and ideal, group ring modulo and ideal. At the end, I find this as a lambda module. So it is isomorphic to lambda modulo a certain ideal. Let's call it I prime. And I know that this is equal. So this is numerically. And this is theoretically, I know that this is lambda I. So I know that I prime is contained in I. And now what you have to show, and I have no time, so I will not give you the details. You must show the converse, that I is contained in I prime. And this is done by multi-precision calculations. The whole issue boils down to certain cyclotomic units being cubes, 9 powers, 27 powers, and you have to prove that. And that we do with using multi-precision calculations. And this is in fact the bottleneck, because to do these multi-precision combinations, we do approximations with real numbers, and the eta n is huge. You see, the eta n is the norm of a cyclotomic field. So F is 100,000. You have to take the norm from a cyclotomic field of conductor 100,000 to something quadratic, and typically you get things the size of the fundamental unit or something like that. And then you are also in the tower, and if you are at level 6 in the tower, that adds another 729 to your degree. So the computations with these multi-precision computations, they become very slow and they get a little bit out of hand. So we can test practically everything, but not quite. Sorry for going over time and not finishing.